Welcome to this video. We are back at our favorite PhET simulation. PhET, this wonderful website, a series of animations provided by Colorado University. So here we are, we've got the string, there's the wrench, I can wiggle this thing up and down, and look at what's happening now. We don't have a window, right? The string doesn't just continue on forever. Instead, now we're going to clamp the end down. So if I make a wave, what's going to happen when it reaches the end? Go ahead and make a prediction. What's going to happen? The wave reflects back. But look, it flipped. See how it flipped? And look, this end is locked down. And again, the wave flips and it reflects. We call this a fixed end. And both of those ends are fixed. What makes them fixed? The particles cannot move. They're not free to be moved around or displaced. But what if I start over and I make it a loose or a free end? Because now, check this out. You see this bead at the very end? Like right here, this last green bead? It's attached to a loop that goes on the pole, and so that loop can slide up and down. So let's see what happens now. It's going to reflect, but does it flip? Oh, look at that. It does not invert, as we say. It inverts on the left side because this end is still, the wrench is still fixed. But this is free, and so it does not invert. Okay. So we've just learned about reflection, but what happens if I do this? I'm going to create two identical waves. Here's the first one. It reaches the end. They're about to overlap. What's going to happen? Watch carefully. You see that? Let's watch again. For a brief moment, these two waves, one is positive, one is negative, they very briefly cancel out. Watch this. Here we go. The waves are starting to overlap. And when they perfectly overlap, right now, right here, they perfectly cancel out. That's pretty cool. So waves can be on top of each other. They can overlap. And if one is positive and one is negative, they cancel. What if they're both positive? What if we have this scenario? Oops, normal speed. There's the first positive wave. And here comes another positive wave. They add together. Hey, super wave. All right, let's speed this up. And now we can do it on the negative side. They're both negative, right? Slow-mo, here they come. Look at that, they make a giant triangle momentarily for a brief moment. They're overlapping, and then they continue moving along. So I want to show this, that they actually do move along. Watch this. I'm going to make a triangle, slow-mo. There's my triangle. And then I'm going to make a square. Let me let this guy move along. Okay. I'm going to now make a square-shaped wave. Like that. So two very different shapes. Where is the triangle traveling, left or right? The rectangle is moving to the right. And look, wait for it. There it is, the rectangle. It hasn't bounced off and changed direction. It still is moving to the right. And the triangle is still moving to the left. And let's watch as they go along the other side. Okay, the triangle is moving right. The rectangle is moving left. They interfere, they overlap, but then this guy just keeps moving and it still remains on top. Okay, the rectangle is going to stay on top. The triangle is going to stay on bottom. And look, there it is. It still is moving across. It's almost like nothing ever happened. So pick one and watch and see how it just, they temporarily overlap and then they continue moving as though nothing ever happened. turn to page 11 in your notes. We describe these phenomena using the word interference. Constructive interference is the adding together of two waves whose displacements are in the same direction. They're both positive waves or they're both negative waves. And here's an example. You've got one wave on top. It's got positive parts and negative parts. You've got another wave on bottom. It's got, again, positive parts and negative parts. But the positives always line up. The negatives always line up. Like this. And so they overlap and they form this resultant. We call it a resultant. The combination is the resultant wave. We also call it the superposition. That's a fancy term. It just means they are overlapping. They're adding together. And that's pretty cool. Constructive interference. So even when they're both negative parts, right? Like this negative and this negative, when those combine, they still add. They're not destroying each other. It's constructive there. Well, what is destructive? That's when they are on opposite sides. It's the canceling out, we'll say, of two waves that are overlapping. They're on top of each other. And they have opposite displacements. One is positive, one is negative. So for example, these guys, this top wave and this bottom wave, are perfect mirror images. So the positive displacement here adds with the negative displacement here, and they cancel out. They destroy each other. So the resultant is a flat line. We've also just seen reflection can occur. When a wave reaches a boundary, the end of the medium, it reflects back the other way. If the end is fixed, right here, that particle can't move at the very end. That means it's a fixed end. What happens? When the wave reflects, the wave inverts. So waves in general invert when reflecting off a fixed end. But like we see, if the wave has this free end, and by free we mean the particle, the rope, the medium, the particle at the end can move, it is free to slide up and down, then what happens? The wave reflects and has the exact same shape. The wave reflects and doesn't invert. It stays upright, you could say. It just doesn't flip. So try these examples. Take note of whether the boundary is fixed or free. And on number 3, I want to give you another example and give you a hint. Let's say we have a wave that looks like this. And that wave is traveling to the right, and it's approaching a fixed end, perhaps. You see this part in purple? That part is out front, and the part in green is trailing behind. So when this wave reflects, we know because it's fixed, it's going to invert. The wave will flip. All right, let me draw that. But how do I know which part is out front? Is it, like this? Whoops. Is it like this? Traveling across? Or is it like this? Here's how to think through that question. The purple part right here, which is now also red, that purple part hits first, and it reflects first. The green part hits second, and it reflects second. So if the purple reflects first, then it stays out front in the lead, and the green part stays trailing behind. So that bottom picture, that's the one that's correct. The important thing is, whichever part is out front stays out front. Like if this purple part is out front leading the way, it will still be leading the way when it reflects. And if you hit a free boundary instead, like this, let's say, here it is moving across, and then this is now not fixed, but maybe there's a pole here, and this string can slide up and down the pole via the loop. What's going to happen? It's going to reflect back. It will not flip, but we're still going to have that circle part leading the way, and then the rectangle will be trailing behind, just like before. The circle part reflects first. It hits first and it reflects first. This kind of rectangular part hits later, it reflects second, so it stays trailing behind.